Today we're going to be learning about the total change theorem. And before we start, I want to take a look at the units. Most of the time they give you the rate, and a rate usually has an amount per time for the units. And what I wanted to talk about first was what happens if you do the derivative of the rate. So if you do the derivative, you're going to get one more unit of time on the bottom. So in this case, we have hours on the bottom for time. And if we were to do the derivative of that rate, our new units would be hours squared on the bottom. So you'll notice the top is not changing, only the bottom is changing. Now, what if we did the integral of our rate? Instead of getting an extra unit of time on the bottom, we're getting one less unit of time on the bottom. So if our rate had these units, then the integral of that rate would give us units that were just gallons. Now that's going to be important because sometimes if you don't understand the question, you could pay attention to the units and it'll help you understand what to do. So if you were looking for gallons as your final answer, and you had a function that had units of gallons per hour, you're probably going to need to do the integral of that function, and then you'll end up with gallons. Again, before we get started, I wanted to review something that we've talked about before, and that is if we had the f prime function, what does that tell you about f? Well, when f prime is above the x-axis, then that means that f is going to increase. And when f prime is below the x-axis, that means that f is decreasing on that interval. Now, how much does f increase or how much does f decrease? Well, it's just the area. Now, I have three examples over here. For my first example, we're looking at the integral from 0 to 4 of f prime of x. Remember that f prime represents all the changes of f. And this integral symbol is kind of like the sum, an infinite sum. So what we have is we have the sum of all the changes. So we're adding up all the changes from 0 to 4. And that would be the area under this curve over here. And that would tell us how much f changed on the interval from 0 to 4. You would get a positive amount. And so you would know that f increased by whatever that amount was equal to. For my second integral, I'm doing the integral from 4 to 8 of f prime of x. And that will give me the area of the blue shaded region, but my final answer will be negative. And what that tells me is it tells me how much f decreased on the interval from 4 to 8, because f prime is negative on that entire interval. Again, f prime tells us how f is changing, and my infinite sum is adding up all those changes. So we're learning how f changes from x equals 4 to x equals 8. So that's what this middle integral is telling us. So this first integral here tells you how much f increased on the interval from 0 to 4. The second integral here tells you how much f decreased on the interval from 4 to 8. And this last integral here basically tells you how much f changed on the interval from 0 all the way to 8. And because the blue region is bigger than the red region, then the net change would actually be a decrease because it decreased more than it increased. So we would expect that third integral to equal a negative number. So you can see we have our number line here, and you can see our x values. We're going from s all the way to t, so those are x values. And if we want to know what is the total change, how much is our f function changing from x equals this first value to x equals the second value? Well, you'd have to do the integral of f prime going from the first value of s all the way to the ending value of t. And that will tell you how much f changed from your time x equals s to x equals t. Now this answer could be positive, it could be negative, or it could be 0. So this change could be an increase, a decrease, or the net change could be also 0. All right, now we finally get to the total change theorem. The total change theorem is going to be the changes that we just talked about plus your starting amount. So that would be the amount that you have at the ending value. We're calling it t. You'd have to take whatever you started with and you add those changes. Remember, those changes were, let's go back a slide. Those changes were the integral of f prime, and you're going from your starting value of s to your ending value of t. But in order to know how much you have at the ending time, t, you have to include the starting amount plus all the changes. And those two things together gives you your total change theorem. So again, we're starting at time s. So you'd have to put your starting amount at that time. That's your beginning value. Plus you add all the changes, and the changes doesn't change. That's the integral from s to t of f prime. So now we're going to do an actual example. Otherwise, this doesn't really make much sense. So let's go to the next page. Here we go. Here's an actual example. Okay, for this example, we're looking at a 31-day period. It says that the rate of change of the number of mosquitoes on a tropical island at time t days is modeled by this function r of t, and the units for that is mosquitoes per day. It also says that you start with 1,000 mosquitoes when time t is equal to 0. So in the beginning, you already have 1,000 mosquitoes on the island. So that's going to be kind of like our starting amount. Here it says, according to the model, how many mosquitoes will be on the island at time t equals 31 days? Well, here's our r of t function. Notice that the units are mosquitoes per day. And our very first slide said that if the units were mosquitoes per day for our r of t function, that if we did the integral of that r of t function, our answer would just be mosquitoes. So we already kind of know that we want to do the integral of that r of t function because r of t has units of mosquitoes per day. And if we do the integral of it, our units will just be mosquitoes. And that's what it wants to know. It wants to know how many mosquitoes there are at a certain time. So how many mosquitoes are on the island when time t is equal to 31 days? Well, we already know we're going to do the integral of r of t. And when t is 31, well, we really need to find all the changes from the beginning all the way to the 31st day. If you look at the actual graph, well, we can see that r is positive until this time right here. So that means that the amount of mosquitoes is going to be increasing until that time. Then we can see that r is negative all the way until this time right here. So we know that the amount of mosquitoes would be decreasing on that interval. And then we can see that r is positive afterwards. So then the number of mosquitoes would be increasing again after that time. So this integral right here represents all of these changes over here from the time t equals 0 to t equals 31. And the 1,000 that you see in front is really just the starting amount. So it's the number of mosquitoes that you had at this time right here. So if you take that starting amount at time t equals 0, and you add all the changes from 0 to 31, then this will equal the amount at this ending time. So this will be the number of mosquitoes that you have at time t equals 31 days. Now, before we go to the next example, I do want to talk about the units. The 1,000 has units of mosquitoes because it's what we started with. We started with 1,000 mosquitoes. The r of t function had units of mosquitoes per day, but when you do the integral of it, you're going to cancel the per day, and the units for that will just be mosquitoes as well. So the first one has the units of mosquitoes, and the second one also has units of mosquitoes. So your final answer has units of mosquitoes. So we just looked at an example where the amount of mosquitoes that we had at the ending time, so that'd be at this ending time right here, is going to equal the amount of mosquitoes that you had at the starting time. So that would be when your time was t equals 0, plus all the changes. Now there was a function that described the changes, but we just wanted the changes on the interval from 0 to 31. So we did the integral from 0 to 31 of our rate function. And because our rate function had units of mosquitoes per day, when we did the integral, it canceled one of the units of time from the bottom. So our final units were mosquitoes for that piece. So that's the total change theorem. That's how it works. You need the starting amount plus all the changes. And that will give you the amount that you have at the ending time. And remember, your starting amount is not always when time is 0. It's when time is equal to whatever this number is here on the bottom of your integral. So the amount here has to match up with the starting time here. And that'll tell you how much you have at this ending time. In this case, that was 31 days. The example that we just looked at had a single rate. And that rate included when the original function was increasing, and it also included when it was decreasing. So it was just one rate, and that one rate did everything. So you can see that the rate was positive here. So that meant the original function was increasing there. Then the rate was negative over here. So the original function was decreasing on that interval. Then the rate is positive over here. So the original function would be increasing over there. So this one rate was all inclusive. The next example we're going to do is going to have two different rates. It's going to have a rate that sand is added. That's called the S function. And then it's going to have a rate that sand is removed. So that's the R function. So you have to combine those two functions in order to get your all-inclusive rate function. Now, if you look over here on the right side, the rate that the sand is added is this red function here. You can see that it's always positive. And the rate that the sand is removed is right here. You can see that it's also always positive on our interval, which we're going up to 6. So that's why to get your all-inclusive rate, you're going to have to take the rate that sand is added and then subtract the rate that the sand is removed. And together, that's your single rate of change function. Now, we're also about to do an example where they just want to find out one thing. They might just want to find out the out amount. So let's say from 0 to 6, how much was removed, and that's it, just the amount that was removed. Well, if I just wanted the amount removed, I would have to do the integral from 0 to 6 of the remove function, which is r of t. Remember, the r of t function has units of cubic yards per hour. So after doing the integral, I'm going to cancel 1 unit of time from the bottom, and the units will just be cubic yards. Now, what if I just wanted to find the amount of sand that was added on that interval from 0 to 6? Well, this integral right here tells me how much sand was added on the time interval from 0 to 6. So this is only the amount of sand that was added. So here's that actual example, and this is our last example. It says that the tide removes sand from a beach at a rate modeled by the R function. And then a pumping station adds sand to the beach at a rate modeled by the S function. It says that both functions have units of cubic yards per hour. And the time is measured from 0 to 6. It also says when time is 0, the beach contains 2,500 cubic yards of sand. So that's kind of like your starting amount. They want us to find how much sand will the tide remove from the beach during the first 6 hours. And they also want you to indicate the units of measure. So the amount that's removed is just going to be this amount right here, and that's it. So the integral from 0 to 6 of the r of t function, because the r of t function is the rate that the sand is being removed. Remember, it has units of cubic yards per hour. So if you do the integral of that rate function, it's going to cancel 1 unit of time from the bottom, and it will have units of cubic yards. So for this question, we just want to do this integral and then stop. But I do want to explain the other integrals that are listed here. If we were to do this integral here, that would tell you how much sand was added during the first 6 hours. If we did this integral right here, so this would just be all the changes during the first 6 hours. If you get positive, that means it increased by that amount. If you get negative, it means that it decreased by that amount. But when you add the 2,500 cubic yards of sand, you're adding the starting amount to all the changes. And so if you did these two things together, that's the total change theorem. It will tell you how many cubic yards of sand are on the beach at this time. So it would be when time is equal to 6 hours. Again, it does say include units of measure. And anytime you see that on the AP test, it means that they will give you points if you do it. And so obviously it means you would lose points if you don't do that. So it's going to be really important to include the units of measure here. Notice it does say how much sand is being removed during this 6-hour period. And so the units are just going to be cubic yards of sand. You don't even really need to know calculus in order to do this part of the question. And so you could actually do just that part of the question, and you would get at least 1 point for that, even if you didn't know how to do anything else on this problem.